Hello viewers, you're welcome to SciEx tutorial, and in today's class we'll be looking at the introduction of limits of functions, and our focus for today's lesson will be on those 3 points. What is limit, which is actually the first principle of way of thinking, why limit, which talks about the importance of the reason for this discussion, and then lastly we'll be looking at the various methods of evaluating limits. So let's go over the first principle of thinking, which is what is limit. Limit actually describes the behavior of function as that function approaches a particular input. For example, you want to talk about the function x squared as x approaches 2. So this is a concept of limit. It tells us how functions behave. For example, price can be a function, right? So you want to know what the price of a particular commodity will be at a certain, at a certain price. You want to know what it will be. You want to know how to make your budget, then that's limit for you. Then we'll be looking at why limit, why the essence of the discussion. So one of the reasons why we are interested in limit is because it is basically the fundamental of calculus. There is no integration, there is no differentiation without limits. One must have to get a basic understanding of limits for one to scale through his or her calculus class. For example, this is not new to us. Yeah, I'm pretty sure this expression is not new to us. So there is no way we understand how to take derivatives without understanding what limits of functions actually are. Another importance of limit is that limits actually help us to understand infinite processes. Infinite processes are things we relate with, are things we interact with in our various classes. For example, you talk about the concept of asymptotes. You talk about the concept of improper integrals. All of these things are things we interact with. But then the basic principle, the first principle of these things is actually limits. And that's what we are discussing today. And one of the reasons, again, why this is so important is that, we sometimes encounter things that we think are useless, functions that are undefined. For example, I give you this. So this is a function that is useless. This is a function that is undefined. But then with the concept of limit, we can make meanings out of this. We can actually look at the properties of this function. So that's why it's so important that we look at the concept of limits. Then the last point, which is methods of evaluating limits. There are many methods of evaluating limits, and all of which I'm going to list for us today. We'll talk about them a little, and then in our next class, we'll see how we actually evaluate limits. So one of the methods we use to evaluate limits is by direct substitution. Direct substitution, we have again by simplification, by L'Hopital rule, and lastly by squeeze theorem. While some textbooks might use sandwich theorem, but it's still the same thing, squeeze theorem. So I'll be talking about the merits and the demerits. I'll be talking about how and when to use these various methods to evaluate limits. Now, for example, I want to solve a quadratic equation that says x squared plus 2x plus 3 is equal to 0. We are basically familiar with all methods that are used to evaluate a quadratic equation. But then, what's the difference between a quadratic equation and evaluating limits? When we want to evaluate a quadratic equation, any of the three methods can work. You can either choose to use the formula method, you can want to use the completing the squares method, or you may want to use the factorization method, except in cases where factorization method may not work. So you are constricted, you're restricted rather, to use only the other two methods. But no, it doesn't work like that for limits. The various methods for evaluating limits are not alternative as it is in the case of quadratic equation. You use a particular method in limit, except it fails, then you move to the next methods. You don't just wake up to use any methods in limits, right? Okay, so let's talk about the how, the when, the merits, and the demerits of each method of evaluating limits. So, to the direct method, to the direct substitution, the direct substitution method is actually the easiest method, fastest method to evaluate a limit. But then you use it only when it works. There are cases when it does not work. How do I use the direct method? It's just to plug in the values. It's just like it said, substitution. For example, I have this. So something like this is supposed to be evaluated with the direct substitution method. All I need to do is I come to x, and if I see x, I put 2, and that's it. So it's very easy. But then it fails in many occasions. What are the demerits? The points where it fails. And it fails where anytime I encounter indeterminate. When I try to evaluate by direct substitution and I encounter indeterminate, it means that the direct substitution fails. Yeah, and what is indeterminate? Any indeterminate of any form. For example, you can have this 1 raised to the power of infinity. You can have infinity minus infinity. You can have 0 raised to the power of 0. You can have infinity divided by infinity. You can have one more. Guess. It's meaning 2 more. Can you guess? Yes. You can have 0 multiplied by infinity. So infinity of any sort, once it is encountered while using the direct method, then it means that the direct method fails. And that would now take us to the simplification method. Method of simplification. So for the method of simplification, this method is subdivided into two other methods by factorization or by rationalization. Yes. So we use the factorization method when we are dealing with polynomials, and we use the rationalization method when we are dealing with radicals, with square roots, right? So depending on the function you're dealing with, that's when you know which of them to use. If it's just a polynomial, then you can use the factorization method to simplify further, and then you make your substitution. If it's something that comes with a square root, then you have to use the rationalization method. It doesn't matter whether you're rationalizing the denominator or you're rationalizing the numerator. It does not matter, but it has to be with rationalization method once you encounter a root, right? And then we'll talk about the L'Hopital rule, which is something I love so much. The most powerful of them all, the L'Hopital rule. Why do I need the L'Hopital rule when I can simply use the simplification method? Yes, I can use this L'Hopital rule when my simplification method fails. Really? Yeah, it can fail. The simplification method can fail. It fails in points where that particular function cannot be simplified further. For example, there are functions you cannot simplify, like the special functions, your trigs, your exponentials, your logarithmic, your hyperbolic functions, Yes. So these are functions that you may not be able to simplify. So when you encounter functions of this nature, then you are expected to use the L'Hopital rule. How does the L'Hopital rule works? The L'Hopital rule works by taking the derivatives, I mean the differentiation of the functions, and then once you take the differentiation of those functions, there you go. It becomes so easy to substitute and get your value. Yes. Wait, am I forgetting anything? No, definitely not. But there is something else, the squeeze theorem. The squeeze theorem is also very necessary, which is what I said. Like you can use you can call it the sandwich. The squeeze theorem comes into play when my L'Hopital rule fails. But can it fail? When does it fail? Yes, it can fail. And when does it fail? It fails when you're dealing with functions that you cannot simplify any further, but cannot differentiate. There are functions that cannot be differentiated, functions that are not continuous, functions that jumps, right? Those functions cannot be differentiated. You cannot take their derivatives. So those functions are functions that you use the squeeze theorem. The squeeze theorem. With the combination of these four methods, there are no limit questions you cannot solve. Every form of the indeterminates you encounter can actually be resolved with either the combination of two of those methods or using a particular method. You can dissolve any limit theorem. Maybe in our next class, when we'll be talking about how to evaluate the limits with each methods as a focus, that will be like a kind of laser treatment, right? So we'll know how to use each of them and we'll know their pros and cons. But then, up until then, I see you later.